Hello everyone, welcome to our machine learning presentation. In this presentation, we are going to talk to you about how we have built our machine learning model for the problematic internet use competition organized by Childmind Institute. So first, I would like to go over the contents of our presentation. In the introduction section, I'll introduce you the competition and its goal. Next, I will talk about our general approach in building the model. Basically, we would talk about the workflow and the pipeline of the machine learning model. After that, I will give an overview of the data that we are dealing with, and as well as how we deal with the data. Then we will show you how we have chosen the model, and then in the model training and validation section, we are going to show you the process that we have trained and improved the model. And then finally, the conclusion. So this competition is organized by Childmind Institute. The goal of this competition is to find a solution to a real-world problem, and it is that excessive internet use among children is linked to mental health issues like depression and anxiety. But the current assessment methods are too complex and inaccessible. So they proposed a method that we should use objective measurements like physical data or biological data to predict the problematic internet use. The goal of this competition is to develop a predictive model to detect early signs of unhealthy digital habits, enabling timely interventions for healthier online behavior. And through this competition, the organizers want to promote a balanced and responsible digital lifestyle for children. So the value that we are predicting in this competition is the Severity Impairment Index. In short, is SII. It is a standardized measure of problematic internet use. The SII represents the severity level of internet-related issues for each individual. As you can see in this table here, each SII values correspond to a severity level of problematic internet use. 0 for none, 1 for mild, 2 for moderate, and 3 for severe. Next, we will show you the general approach. So basically, our workflow is very standard and simple. We start off with data preparation, then we proceed to modeling, and finally evaluation, finally submission. After submitting our models and answer, we will analyze the results and then revisit previous steps to try improve the model. So before we work with the data and the models, we have to define a pipeline, a general pipeline. So here's our basic pipeline. There might be some changes, but this is the general pipeline. First, we will do some data cleaning and feature engineering. After that is imputing the data, training, and then evaluation. All right, now we are going to have an overall look of our data. So I will divide the given data by their purpose and then their type. First, we are given the data set, and I will divide the data set columns by their purpose, which is for training, which are the features columns, and then the label columns. And in the given features, we have two types of data. First is the time series data, which is the accelerometer data, and then the tabular data. As for the labels, we actually given two types of labels. First is the SII values, and then the PCIAT questionnaire, which we will use to derive the SII values. So in this competition, we would like to keep our model simple and lightweight, and it takes a lot of time and resource to process the time series data, so we just omit that type of data and we will just only use tabular data for training. Next, we're gonna have a look at the features that we are working with. In the given data, there are 60 different features, and the included data types in the features were categorical integer, string, and float values. And by default, the features, it was divided into different groups of measurement methods, which are physical, for example, physical measurements, questionnaire features, and some biological measurements features like the bioimpedance measurement. Now for the labels, we actually have two different types of labels instead of just one. The first one is our target label, the final target labels, which is the SII values, which I have mentioned before. Another type of labels is the PCIAT questionnaire. It is the full name is Parent-Child Addiction Test. Basically, in this questionnaire, there will be 20 different questions. Each question will have 6 answers, and the participants will have to pick one of those answers, and then the final score will be the sum of the 20 question answers, and then the total PCIT score will be converted to SII values in the corresponding range that I'm showing here in the slide. Next is a very important part of our workflow is the data processing step. So we will basically show the data processing methods that was used in all of our models. The method was applied across all models with some variations and change, but generally they hold the same idea. First, we will have to deal with the missing labels. So here we have drawn out a missing and to available data ratio graph. So by having a closer look at the missing to available data ratio diagram, we can see that there are a lot of missing labels, which are the SII values, and the 20 PCIAT question, which are also the labels. So for some more insight, we have drawn a diagram of SII distribution. And as you can see that there are a lot of missing labels. There are 31% of the data that don't have the label. So at first we was gonna use unsupervised learning methods to fill the missing labels, but in the end we wanted to keep our data as true as possible, so we decided to drop all data that have missing labels. We drawn a line where we will be trimming the data. We will delete all data with missing SI values as well as missing PCIAT values, because SII values is derived from the PCIAT questionnaire result. So if a PCIAT questionnaire result is missing, it means that the SII value might be false. So here is the missing to available data diagram after we have removed all data with missing labels. And before trimming, as you can see, there are almost 4,000 rows, and after trimming there's only approximately above 2. After that, we also have to deal with features that have high missing ratio. We decided to remove all features with greater than 40% of missing data after when we have trimmed all the data with missing labels. This also means that we want to keep the features with more than half of the data. We do this because if we try to impute features with high missing ratio, we are basically making up the data, and it might be very biased and doesn't generalize very well with real-world data. And next, for the string data, we are going to either remove them or encode them, because the models we had in mind when we looked at the data are the models that can only process numerical values. After dealing with the missing values, we are going to remove the noise. And to handle with the noise, we decided to use quantile capping. Well, at first we did try to remove the noise and finding the threshold to remove the noise manually, but that is a very tedious task. We decided to get the data in the range of 98% percentile by capping the left side of the distribution at the first quantile and the right side of the distribution at the 99th quantile. So generally, we did some quantile based filtering capping for all features in the data. Here are some features, the distribution of features, some features before and after capping the data. As you can see, at first the distribution were very skewed, and then after capping, it becomes very neat and very clean. But of course, we didn't remove all the noise. We decided to keep some of the noise, as you can see in the box plot here. Some of them, they are very dense. The frequency of noise is very dense outside the interquantile range. So this means that the noise might capture some extreme case or special case in real-world data. So that's why we decided to keep it. Also, there is another type of noise, which are the unreasonable values, like physical weights is 0 kilograms, and such kind of values. We decided to, instead of removing them, we decided to convert them to NaN values and for some imputation later on. After having cleaned the data and do some exploration on the data, we are going to do some model selection. So we did take several models into consideration. So we had to draw out this table right here to see what model we should choose. And the criteria column in this table is created based on the nature of our dataset. Now, first we considered SVM and logistic regression. The problem with SVM is that it doesn't have built-in support for multi-class classification, which we need for our task, although it can use for that purpose, but it requires complex implementation. And then we considered logistic regression. It's a lightweight model, simple, efficient, but it has the same problem with SVM, is that it requires extra step in data transformation, which is scaling, and both of these models are sensitive to outliers. Next, we also considered naive Bayes classifier. The problem with this is that it does not perform well with complex data, like the dataset that we are having, with a lot of features. And then finally, we decided to choose tree-based model. We chose a random forest classifier and XGBoost because first, these models can work well with small dataset. It is robust to outliers and it have native support for multi-class classification. The reason we choose two of these models instead of just random forest is that these are the complementary models, and we will talk about that later on. Now, for the main course, we are going to have model training and a validation. So we have made a lot of submissions, but basically there are 3 main versions, and each versions have a big change and a new approach, a core idea. So I will go over some of the versions that have made big changes, and we consider them milestones in our process of training the models. Before going into the model training process, we need evaluation metric that we are going to use for this contest. So the evaluation metric used here is the quadratic weighted kappa score. As you can see in the equation shown in the slide, the fraction term, WO over WE, represents the disagreement between the predicted value and the expected value. O is basically a confusion matrix between the predicted value and the true value, and E is the confusion matrix between the true labels and the true label itself. Basically, O over E is the disagreement between predicted value and the expected value. And the weights here, the W terms, play a role in making us a distinction between different kinds of mistake. Without the weights, say the model predicting 1, the label 1, but mistake it with 2, the consequence would be the same as mistaking 1 with 5. But with the weights, mistaking 1 with 2 is less severe than mistaking 1 with 5. By using 1 and subtract the term here, you get an agreement metric instead of disagreement. Alright, so let's step into our first model. In the first model, the core idea here is that we don't directly predict the SII values, but we predict each individual PCIAT question first, and then we sum it up and then convert it to SII values. The data processing step is the same as what we mentioned before. The imputation method that we use is KNN, K nearest neighbors, with 5 neighbors. We use these methods because it can capture the complexity of the data. And also, we choose this from trial and error. We try different methods like median and mean, but this performs the best. So in this model, we basically built a random forest for each PCIAT questions. Each forest have 100 trees. So in total, we built 2,000 trees for 20 questions, and after that we're going to sum up the predictions to convert it to SII values. Well, this is the first model we have trained, and the test set accuracy is actually the validation set is 0.9, which is too high. And you can also see a problem here is that there is no label 3 in the confusion matrix. And the problem probably stems from, it definitely stems from the way that we divided the train and validation set. And we basically used the last 100 values of the data for validation and the rest for training. And so the last 100 values of the data doesn't have any data with label number 3. Alright, we will go straight to version 2.0. In this version, instead of using the idea that we predict the PCIAT question individually, we directly predict the SI values. And in this version, we also resolve the problem of the previous version by using stratified sampling for training. And to tune the hyperparameters, we started to use a grid search. Here are the changes that I just mentioned from version number 1. And there's also no change in the way that we process the data. So we have used stratified sampling here to make sure that all the labels in the data in the training set exist in the validation set. And we use stratified sampling also to make a more accurate validation when we tune the model. And we also do this to make sure that the model will have better generalization. So in this version, we implemented a grid search model with cross-validation with 5 votes per combination of parameters. Instead, so we no longer have to tune the model by hand like we did. And of course, the grid search is guided by the kappa scorer to find the best model, the model that has the best quadratic kappa score. So here's the evaluation result. As you can see, there's a big gap between the training score and the validation score. This shows that the models might be overfitting. However, the test score is still improved from the previous model. We can explain this because in the previous model, when predicting separate PCIAT values, the error might accumulate through each prediction and it builds up and get larger instead of predicting the SII value directly. And also, if you look at this confusion matrix here in the validation set, you can see that the prediction tend to favor the labels with a higher number of data. And we will try to fix this in the next version. So in version 2.1, we tried to make use of string data, and we also introduced balanced weight. As we talked about as mentioned, our model favors the labels with more data point. So what we do is that we introduced balanced weight. By doing so, when the model mistakenly classifies the labels with fewer data points, it gets punished harder than mistakenly classify the labels with more data point. And then we also tried to make use of string data, which were all season data. At first, we tried to use hot encoding, but we realized that the models that we are using are tree-based models, so it handles ordinal data similarly as nominal data. And here's the evaluation result for version 2.1. As you can see, there is a smaller gap between the training set and the validation set score, and also the validation set score also increased significantly. And by looking at its confusion matrix, we can also see that the predicted labels are less skewed to the left of the confusion matrix. And the test score also increased significantly from the previous model, from 0.3 to 0.4. So in the next version 3.0, we made a lot of change. We basically rebuilt the whole code. So we add more noise and we use a new technique optimizing the SII boundary. We also changed to classifiers, regressors instead of classifier. And we also use k-fold cross-validation during training. So when we were rebuilding the whole pipeline, we realized something. When we apply quantile-based filtering for all the features, we are removing some of the very important noises, which might reduce their generalization on new data. Here is the physical height. For example, physical height before and after capping. You can see that some of the relatively useful noise is removed. Instead, what we did was that we only perform noise capping on the data with extremely skewed distribution, as you can see right here. And these are the distribution after it got cleaned. You can see that it became very neat and tidy, and still have some important noise remained, not all completely removed. So a key technique that we use to improve our models here is called decision threshold tuning. Basically, instead of directly predicting the discrete SI values, we will first predict the continuous SI values and try to round them up. And we will have to find the criteria to round those values into the correct classes. So I have drawn these initial decision boundaries here. They have the values 1, 2, and 3. As you can see, if the dots are smaller than 1, it will be put into class with label 0. If the dots are greater than 1 and smaller than 2, they will be put in class 1. But the problem here is that the initial threshold are not in the best position. As you can see, it does not separate the classes correctly, so it will have a very low quadratic kappa score. What we want to do is we want to find its better position that increases the quadratic kappa score. And by using some optimization method, we can find the new positions for the decision thresholds. If we move all the threshold to the right with the right amount, we get new positions that separate the data points more correctly, and it will give a higher kappa score. So to do this task, we use a extreme gradient boosting regressor with L1 and L2 normalization in reg alpha and reg lambda parameter. Instead of separating train and validation set before, we will use the whole training set, and we will perform k-fold cross-validation. And in this cross-validations, we also collect the out-of-fold results, so we can later process it. So here's the evaluation result for version 3.0. As you can see, there's a very big gap between train and validation set score. This indicates that the model is overfitting, but we will try to fix it later on. What's interesting here is that the validation score before tuning is 0.38, increased to 0.45 after tuning. And when we submit this model, the test score is 0.42, which is an improvement from the previous model. So to mitigate the problem of version 3.0, we decided to ensemble a random forest and an extreme gradient boosting classifier. And we also implemented feature engineering. So in previous models, we tried to see how far we can go without using feature engineering. But at this point, we decided to use some feature engineering to improve our model. We made new features based on their correlation, specifically features with high correlation with each other, to try to create features with greater impact on the model. And we also use domain knowledge, which in our case, we are not experts, so it's basically just intuitions. For example, we just divide a bunch of different types of mass over the total body weight to try to find some features that might have significant impact on the model. As I mentioned before in the model selection section, we chose random forest and XGBoost because they are complementary models. Well, this is because there is a trade-off between those two models. Random forest, it is very good, it has good stability, but it cannot capture complex data. XGBoost, however, it can capture complex data, but it tends to overfit. So when we try to combine these models, it cancels out and gives us a very balanced predictive model. So since version 3.1 is pretty much the same as version 3.0 with an extra random forest regressor, we also use the same tuning method. And the method that we use to find the threshold that maximizes quadratic kappa score is the Nelder-Mead geometric optimization method. It's basically a method to find local minima without having to find a gradient. And it's a simple and quick calculation. But the problem is that it doesn't support a maximization. So we have to minimize the negative quadratic kappa score. And here's the result for version 3.1. As you can see, the validation score increased significantly after optimization. And the submission score is 0.445, which is a relatively good score. So our team decided to settle with it. So here's our final model. As you can see, it's a very straightforward model. But the most important part of this model is the ensemble between random forest regressor and an XGBoost regressor and the decision threshold tuning part. We think that we can improve this model by using more data, which is the time series data. In this model, we have yet to use the time series data, and we believe that if we use it, we can improve the prediction more. Here is our model training record. Not all the models are included in here. We only include the submissions with significant change or a moderate amount of change. Small changes like changing a single parameter is not included in here. And the model, our best model, is version 3.1 with a public score of 0.445 and a private score of 449 shows that it has good stability with different data. And this model has given us the rank of 162 in the competition. What surprises us the most is that the simpler model, version 2.1, performed the best with private score of 0.45, although the public score is only 0.403. This shows that this model would perform better with more data. So that's all about the journey that we have went through to build the model for the competition. Thank you for listening.